What's up, team? Today we're talking about angles that are formed by tangent lines and secant lines. Let's go over some terms. Let's get on the same page and do a few examples. Here in red, we have a circle. It's centered right here. It didn't give it a name. Let's call it circle X. And we have some lines going through it. So some of these lines are familiar with. Some of them might be some new terms. Let's make sure we're dialed in here. So segment BC right here, from B to C, these points are both on the circle, and it goes through the circle. It touches the circle twice. That's called a chord. It's called a chord. But if you extend that chord into a line that goes forever in both directions, well, we call that a secant line. Secant, S-E-C-A-N-T, secant line. And we're going to be using these today. I know that might be new for us. Similarly but different, technically it's slightly different. Segment AD, so that's the segment from A to D with endpoints. It doesn't go forever in both directions, but it does go through the circle. We call that a tangent segment. That just means it's kind of chopped off at the ends and it doesn't go forever. Not a hugely consequential thing, but it's true. Okay, here line EF is a tangent line. E to F, and it goes forever in both directions. Tangent line, it touches the circle once and only once. Similarly, segment EF is a tangent segment. We've studied those previously. From E to F, if you cut it off right there, touches the circle exactly at one point, even if it were extended. Okay, so that's some of the terminology that we're going to be using. Here we go. This blue situation here, we have circle X again. We have two tangent lines meeting here at a common point B. So BA is a tangent line, BC is a tangent line. We've previously studied a tangent segment theorem that would say that A, B, and BC have the exact same length. That's cool, but that's not what we're talking about today. Today, I want to figure out what the measure of this angle here is, angle ABC. And the only piece of information we have, well, I guess we kind of have two pieces of information. We know that AB and BC are tangent lines. That's given. We also know that the arc measure of AC here is 100 degrees. That's given as well. From just those pieces of information, we're going to figure some things out. So the first thing we need to notice is, or remember, I suppose, is that the whole circle measures 360 degrees. We can break this thing up into two different arcs. One of them is this minor arc AC. One of them is the major arc ADC. Right? So the big stuff plus the little stuff needs to equal 360. If the little stuff equals 100, the big stuff from A to D to C must be 260 degrees. Again, that's from A to D to C. All right, now we're going to use that information up there. We need that length of that major arc. And there's a simple formula. Check it out in the notes for a more detailed description. I'm going to show you how to use it though. The formula to find this angle is we take the major arc. We subtract from it the minor arc. So that is 260 minus 100, which is 160. And then we take that 160 and divide it by 2. So 160 over 2 is 80 degrees. This theorem here says that the measure of angle ABC is 80 degrees. So again, a more detailed description in the notes, but this is how to use it. Major arc minus minor arc, 260 minus 100, you land it with 160. You take that 160, you chop it in half, and you get 80 degrees. My claim here is that the measure of ABC is 80 degrees. One more thing to pick up here. Notice that the minor arc and this angle ABC are complementary to one another. They add up to 180 degrees. Not a coincidence. That'll happen every time, and you can even use this to help you solve problems. For instance, we didn't even technically need to find that 260. We could have seen the 100 and been like, oh, well, I know that these are complementary, so this must be 80. So kind of keep that in your back pocket. Sometimes that'll be really helpful. Okay, let's bounce over here to the purple circle, the last example here. Here we have two secant lines. Remember, a secant line that we discussed over here is a line that goes all the way through the circle, touching it twice. So we have a secant line CA that goes on forever in both directions, and then secant line CE that goes forever in both directions. Of course, both of them meeting here at point C. The task of this here problem is to find the measure of angle BCD. I want to find that angle right here. The way that we do this is super similar to what we just did with the tangent, the two tangent theorem here. So with two secants, you're going to take the two arcs that are intersected by our angle. Now, it's a little different because here there's only two arcs, period, end of story. Over here, we kind of have 4, right? There's AE, there's ED, there's DB, and then there's BA. But we're only interested in 2 of them. We're only interested in the arcs that are intersected by our angle. In this case, it's AE and it's BD. These are the ones that are intersected by our angle. So basically all you're going to do is take the big one, subtract from it the little one, and divide it by 2. Just like what we did over here, but slightly different, slightly modified, right? It's a smaller angle because if it were the tangent, it would be opening up to the whole entire circle, just touching it once. So let's walk through it. 60 minus 10, that's 50. We're going to take that 50, that result here, chop it in half, and we get 25. That's it. End of story. The measure of angle BCD is 25 degrees because of what we just discussed right here. Okay, more details, kind of more spelled out in the notes, but this is how to solve these types of problems. Okay, angles formed by tangent lines and secant lines. Give it some practice. Let me know if you got questions. You got this.